So in traffic crash data, there are lots of correlations. To start with, there are spatial correlations, temporal, and there could be correlations among crash types. So the spatial correlations means there is a corridor comprised of various intersections and the segments. So since the traffic volume entering a corridor is almost the same, that means it's logical to assume that the types of crashes happening on the intersections of those corridors will also be the same. So the spatial correlation accounts for those similarities. It could be between the intersections, maybe between the segments, or this is the micro level. The macro level could be TAZ, could be county, and other things. So the second type of correlation is temporal correlation. This accounts for all the changes that happen during the years. So the crashes are affected by the socio-demographic changes happening around the environment, and also maybe there were the lane width previously was 12 feet, and then maybe it was reduced to 11 feet. So those changes are accounted in the temporal correlation. And the third type is also called as multivariate, where we use the correlation between different crash types or crash severities. Maybe there is a correlation between rear end and head-on crashes happening at the exact same intersection. Next, please. So in this presentation, we are going to discuss about development of 8 models. All of them will have temporal correlations in different forms, which it's going to start from very basic and go up to really complex model. And there is also one model which we are proposing. It's a combination of autoregressive with a lag 1 and the time varying parameters. So the steps for the whole process goes like this. So first we collect the data, and the data is from traffic analysis zones. That's a TAZ from Irvine in California, and then we develop the 8 models, and then we do some comparison and evaluations. But the comparison and evaluations will be reserved for the next presentation. This presentation we are only going to focus on the development of 8 temporal models. Next, please. So the data collection, just briefly, it's from the 203 TAZs. So that's our sample size, 203 TAZs in the city of Irvine in California. The crash data is from 10 years. So from 10 years we expect that we can effectively incorporate the temporal changes throughout those years which affect the crashes. And there were other covariates also, because since we are using the TAZ, so we are using socio-economic factors, some transportation related information, and other environmental factors. So the crash data is comprised of fatal and injury collisions only. Since we are not including PDO in this case, because PDOs are underreported. That means a lot of crashes happen where there is a property damage only, but still people do not report this to the police, maybe due to the hassle. So those are not included because they are not the clear picture of what's happening on ground. So, and here we are using, for the whole thing, we use 2 softwares. One is R and other one is Winbugs. Next, please. So now we are gonna start the modeling stuff of the temporal models that we used. Next, please. So these models are, so whenever instead of a simple model, whenever we try to incorporate some correlations, we build up a hierarchy in the model. So this is implemented in the full Bayesian, which will be covered in later presentations. But here we can see that this one, the Y, is the crash count happening at the place. This is the observed crash count. And the theta here, it's the Bayesian crash count that will be predicted, which will be calculated by our model. And usually whenever we are using Poisson distribution, Poisson model, that means we are assuming the distribution to be Poisson. That means the mean is equal to the variance. It's normally the case in case of crashes, but sometimes it may not be the case. But again, we are using the crash count, and since we are using the model is crash frequency, but still we are using it a crash rate model. And here the E term is actually representing the exposure. So exposure could be of many types. It could be AADT in case of intersections. It could be the length of the segments in case of segment. But since we are using TAZ, so we are using the exposure of daily average daily vehicle miles travel in the TAZ. Next please. So this is our first model. Earlier we saw that the model it's a Poisson model, and here we can see that it's a log normal model. It's used because to accommodate the extra variance or variability that comes into play because of so many factors. But if we are using only Poisson model, that means we are assuming the mean equal to the variance, and then our model is not correct. So here we can see that the beta is the intercept, and beta k and xk, these are the vectors of independent coefficient, and the other one, the x, is the covariates, whatever covariates we are accommodating in the model. So before we select the covariates to actually account for the model, we usually run the model, a basic model, just to see that whatever we remove the covariates which are really multicollinear. By multicollinear we mean that it's a 100% correlation. That means a value of one variable could be used to predict the value of another variable. So we need to remove those. So after removing those, we are only considering the variables which are not collinear. And here we can see that there is a phi. Since this is a temporal model, but still we are having a special error term. We are using this because we do not want, since we are testing only the temporal, we do not want a spatial correlation to affect the results or accuracy, the prediction accuracy of our models. So we take this out so that we could analyze what is the real temporal correlation. So in this model, this is called the independent over time random effects. This term here and this one here, they are not the covariates from the actual data. These are the random terms which are included to account for the heterogeneity which has escaped from these coefficients. So that's why we are including these. So next please. So from the previous model, this second model, this is different because of this error term. In the earlier version, the error term was independent from the time. Here we can see that the error term only has the subscript I. I refers to the location, as in the previous slide. I refers to the location, and the t is not there. That means the random effects is fixed over time in this case. So the third model, where we can see that we are introducing a linear time trend. That means we are saying that there should be a proper covariate which is only dedicated to the time. So let's say the time is varying per year. Since we are using 10-year data, so the time is equal to 1 for the first year, the whole equation, and then 2 for the second year. Here we expect to catch the time trend, the linear time trend. Next please. So this model, the fourth model, here we are increasing the complexity of the model. As you can see, the beta t is already there, but we are introducing another coefficient which is changing with the square of the time. That means for the first year it's 1, for second year it's 4, for third it's 9. So we are using these models to find that whichever model is fitting our crash, the observed crash data better. That means maybe it could be better in the the hotspot identification also. So the fourth model is the varying intercept model. Here we can see that in case of this model, the intercept was not varying with time, but here it's varying with the time. This is an effort to capture the changes with the time, but intercept time we can see that the intercept here is changing linearly with the time. So in this case it was not there, and here we are changing the time. So maybe we are expecting that if there is a linear change in time, then it could be captured in this one. Next please. The sixth model is the varying coefficient. So in the previous case we were changing the time, the time 1 year, second year, linear time only for the intercept. But here for all the covariates that we are having, maybe it's the environmental covariate, maybe it's the geometric covariate, we are assigning a time trend to that covariate also. So we are directly linking the value of that covariate in that present time and changing it for different years. In the seventh model, this accounts for the autoregressive one lag. That means it's a simple model, but instead of just using the linear trend for temporal correlation, it also accounts for the year that just passed by. Let's say we are talking about the 4th year. So this model also accounts for the changes that occurred in the 3rd year, one preceding year. The lag 1 here symbolizes the 1 year. And if there are other models also like lag 2 and others, but for simplicity we are just using lag 1 in this case. So the 8th model is the combination of the varying coefficients and the autoregressive model. So here we can see that the coefficient as well, all the coefficients are changing with time. The intercept is changing, the covariates are changing, and the error term is changing, and they are also taking into account the changes from the previous year, since we are using the AR1 model.